Alrighty, welcome to the last function, and the last function is the tan function. And the tan function is weird. Let's go. So if we jump into Desmos just to get a sense of the function, and we type into it y is equal to tan of x, what the heck is this math? Well, the tan function isn't defined half of the time. Let me set my x label onto pi's. In fact, actually, let's set my thing to pi on 2. Yeah, look at that. That looks much nicer. Okay, so you can kind of get a sense of how awful this function is. So this function has, like the other functions, it has an infinite number of x-intercepts, but it's got an infinite number of other things. It's got an infinite number of asymptotes. X equals pi on 2 is an asymptote. X equals 3 pi on 2 is an asymptote. X equals 5 pi on 2 is an asymptote. X equals 7 pi on 2. And that's just going in the positive direction. Going in the negative direction, we also have x is equal to negative pi on 2, and so on and so forth. So you can see a lot of these functions. So not only does this function have infinite number of x-intercepts, it also has an infinite number of asymptotes that recur. And the other thing you'll notice is that the other functions we dealt with, their basic period was 2 pi. This one's basic period is just pi. Why? Because tan is different. Tan is not like the other functions, and we've got to be really mindful of that. Sketching tan is not like sketching the other functions. Okay, so now that we're happy with that, let's get rid of all of these asymptotes so they don't confuse us later. But let's do the same thing we did last time. Chuck an A out the front, chuck a B on the inside, and see how it changes. As we change the A value, it does change the shape, but the asymptotes stay the same. When we get a negative A, it does reflect. But apart from that, it's looking all right. For the B value, on the other hand, this is going to change our period. And because our basic period is pi, the rule isn't going to be 2 pi over the absolute value of b, it's going to be pi over the absolute value of b. So the amplitude's not really something we worry too much about. It is going to change a little bit about the shape, but in the end, it's not something that's going to worry us in a sketch. Alrighty, so let's go through some notes. So the intercept, the A value is the amplitude, but again, we're not really worried about it. So given y is equal to A tan of bx, the A doesn't really have anything. It is the vertical dilation, but there's no real analog to either of the other things. So the most important part is going to be that the tan function starts with an x-intercept at 0, and then it has one after each period. So its period is equal to pi on the absolute value of v, and that's going to be basically our function that we're going to be dealing with. Now, with this, the other thing is that we're going to have asymptotes are going to be at x is equal to, and then it's going to be, we're going to have x-intercepts. That's the more interesting one. X-intercepts are going to be at 0, and then 0 plus the period. So 0 plus period, 0 plus 2 period. Let's just call period p for a second. It's going to be 0, 0 plus 2p, 3p, 4p, and so on and so forth. All right, because we haven't moved it anyway. But for the asymptotes, they're going to be at x is equal to, well, they start off at half of p, p on 2, and then they repeat after every p as well. So plus p, plus 2p, plus 3p, so forth. It's going to make more sense when we do it visually. Alrighty. So determine the x-intercepts and the equations of the asymptotes of the graph of the following functions, and then we're going to have a go at sketching them. So we've got 3 tan of x. Well, A doesn't really mean anything, so we can disregard the 3, and the period's just going to be, because the B value is equal to 1, that means the period is going to be equal to pi on absolute value of B, which is pi on the absolute value of 1, which is pi on 1, which is just pi. So the period's going to repeat every pi. The fact that it's got a 3 in the front doesn't really matter. So let's do my x-intercepts first. So there's going to be 1 at 0, then there's going to be 1 at pi, and then there's going to be 1 at 2 pi, and then 1 at 3 pi. Alrighty, and we could go backwards, do negative pi, negative 2 pi, negative 3 pi. Alrighty, the asymptotes are going to appear halfway in between. So halfway between 0 and pi is going to be pi on 2. Halfway between pi and 2 pi is going to be 3 pi on 2. Halfway between 2 pi and 3 pi is going to be 5 pi on 2. And that pattern's going to repeat as well. So let's draw vertical lines for the asymptotes. And the basic tan functions is actually an increasing function. It just increases constantly. So it's going to go up to infinity, and then it's going to come up from negative infinity, and then back up to infinity, down from negative infinity, up to positive infinity, down from negative infinity, and then up to positive infinity. And that's going to be the tan function. So you can see the x-intercepts are just going to be at regular intervals, and then the asymptotes are also going to be at regular intervals. Alrighty, let's do the second one. So the second one is negative tan of 2x. Now, just as a reminder how the negatives work, if we make b negative, it reflects it in the y-axis. And when we make a negative, that reflects it in the, let's make b more reasonable, it's going to reflect it. So it makes it decreasing. So either making a or b negative is going to make it a decreasing function. Weirdly enough, making both of them negative will make it an increasing function again. Anyway, so we've got negative. So this negative just tells us it's been reflected in x-axis. And the period is going to be equal to pi on the absolute value of 2, which is just pi on 2. And now I can sketch. So our first x-intercept is going to be at 0. The next one's going to be at pi on 2. The one after that, pi on 2 plus pi on 2 is just pi. And we might do one more at 3 pi on 2. The asymptotes are going to appear halfway in between. Halfway in between pi on 2 and 0 is pi on 4. Halfway between pi on 2 and pi is 3 pi on 4. Halfway between pi and 3 pi on 2 is going to be 5 pi on 4. Draw my asymptotes in. Now, if I didn't have the reflection happening, well, it'd be increasing just like before. Oh, I've drawn an extra one in there. I was wondering why it didn't line up. So normally it would look like this, and then like this, and so on and so forth, but it's been reflected. So it's actually going to be pointing downwards and then coming down from the top, flattening. Oh, let me move my pi on 2. Going down to negative, coming down from the top, hitting. Alrighty, and if we continued out this way, it would also look like that. So this is the function y is equal to negative tan of 2x. Alrighty, so let's sketch the graph of y is equal to tan of x on 4 over the domain negative 4 pi to 8 pi. Alrighty, lucky last one. This time we've actually been given a domain, and the b value is slightly more interesting. So b in this case is a quarter. So working out the period based on that is going to be slightly more interesting. So we're going to get the period is equal to pi on a quarter. Pi divided a quarter, well, that's pi divided by a quarter, which is really pi times 4 on 1, which is just 4 pi on 1, which is just 4 pi. So the period's going to repeat every 4 pi. So let's drop our axes. And you know me. Oh, in this case, I actually need a bit more x because I'm going to be going out to negative pi on 4. So out here, that can be negative 4 pi. That's 0. That's 4 pi. And then this can be 8 pi. And those are going to be all my x-intercepts, because it's repeating at that. Now, halfway in between is going to be my asymptotes. Halfway between 4 pi and 0 is going to be 2 pi. Halfway between 4 pi and 8 pi is going to be 6 pi. And halfway between 0 and negative 4 is going to be negative 2 pi. And so I can draw my asymptote lines out. You can see it hasn't been reflected in any shape or form. There's no negatives a value and there's no negative b values. So it is just going to be an increasing function. From here, we can just sketch. So it's going to look something like that. And it's going to look something like that. And then it's going to finish there. Because we've been given a domain, we don't want to go past the domain. So this one here is it's still going to be increasing. And there you can see there's our completed graph. And there we are. Give it a label. The axis 2. I just labeled the x-axis y. Don't do that. X on 4. And there is our function. Alrighty, so that is how we sketch tan functions. See you in the next one. Goodbye.